Hello dear student, today I welcome you to a new topic in chemistry, which is shapes of molecules. What is shape of a molecule? Shape of a molecule means how are the bonds in a covalent molecules are spread in the space. In this topic today, I'm going to show you different types of shapes of molecules and explain why they get these shapes. The formula of the molecules we write may be molecular formula or even a structural formula. They do not represent shapes of their molecules. So today we're going to start with some examples first. Here you see the first one is written beryllium chloride. Beryllium chloride we write as BeCl2. Here you see its shape, two bonds spread just opposite to barium atoms, giving the linear straight shape, which is a linear shape with the bond angle 180 degree. And here the boron trichloride. This is the second boron trichloride. This gets trigonal planar shape, where you get boron at the center and three chlorine atoms surround this, keeping equal distance, keeping the bond angle 120. And here you get water, as very common water. We write as H2O, but its shape is bent or V shape, and that with bond angle 104.5. Here you get methane. Methane gets tetrahedral shape with bond angle 109.5, and at the center you see carbon atoms. PCl5, phosphorus pentachloride, we say phosphorus at the middle, and this get in phosphorus pentachloride we get two different angles. One is 90 degree, another is 120 degree. And here the last one is octahedral shape. We say this is sulfur hexachloride. This is sulfur hexachloride. This gets octahedral shape. Each of the bond angles is 90 degree. We can explain shape of a molecule or predict possible shape of a molecule with dot and cross diagram of the molecules. So first we need to draw dot and cross diagram of a molecule to explain or to predict its shape. Mainly the shape of a molecule depends on electron pairs around the central atoms of the molecules. Here in barium chloride, the central atom is beryllium, and you need to look at how many electron pair around central atoms to explain its shape. Same for boron trichloride. Boron at the center, you need to know electron pairs around the central atom, boron here, and here's oxygen, here's carbon, and here's phosphorus, and finally you would get sulfur. So we first need to draw the dots and cross diagram to know how many pair of electrons around the central atoms. I'm going to explain shapes of the molecules in terms of VSEPR, means valence shell electron pair repulsion theory. With this VSEPR we mean the electron pair around the central atoms only, because the central atoms actually dominate shape of the molecules. And when the electron pairs around the central atom repel each other and they keep maximum distance, and they automatically get a shape. I can explain VSEPR with a very simple example, which is suppose I'm an atom, central atom, and I get two bonds around me, two bonds, my two hands are two bonds, and in these two bonds I get two pair of electrons. Here's one pair, this marker, another pair of electrons, and when they repel each other, so certainly they won't be close, they would be at maximum distance. And when these two pair of electrons keep maximum distance, so they will be like this, certainly like this. So consider I'm central atom and my two bonds here around me keep maximum distance. So this causes the shape of the molecule to be just linear. If we go for explaining shapes of the molecules, let's first start with the molecules which do not have any lone pair of electrons. Our first choice is barium chloride. Central atom, beryllium, doesn't have any other electrons, that's two pair of electrons. So if this pair of electrons repel this pair of electrons, certainly they will keep maximum distance, and they would have certainly this shape, a linear shape, keeping maximum distance. Our next choice is boron trichloride. This gets a trigonal planar shape with bond angle 120. Why? Look, we can explain easily with this dot and cross diagram. See the central atom, boron here, gets 3 pair of electrons. All 3 are bond pair, which means they repel each other equally. When these electron pair repel this electron pair, and this electron pair also repel both of them, then they will certainly keep maximum distance. And if they keep maximum distance, we certainly would get this shape. And we can consider these 3 markers as 3 bonds. When each of them repel each other equally, certainly they will keep maximum distance. The possible maximum distance would be 120-degree bond angle. Look, this gets this shape. This is certainly planar, and this is a trigon. The next one you see methane with this shape. This is tetrahedral shape with bond angle 109.5. So why this gets this shape? Here you see dot and cross diagram of methane. At the center we get carbon atoms, 4 bonds around the central atom. When these 4 pair of electrons repel each other equally, and they want to keep maximum distance to minimize the repulsion. That's to have less stress in the molecule. I can also show these 4 bonds with this marker. If you get 4 bonds around the central atom, and you may think that this bond could be 90-degree, maximum 90-degree. No, here's this. If this is a planar shape with 4 bonds, that would be maximum bond angle would be 90-degree. But if you make it 3-dimensional shape, that is this 3-dimensional. Look now, this is 3-dimensional shape. We call this tetrahedral, and bond angle is more than 90-degree, which is 109.5. So this molecule is automatically gets this shape for minimizing the repulsion. Now I'm going to explain 2 shapes together. One is ammonia, another is water molecules. They are 2 together because both of them have lone pair of electrons, other than bond pair. Lone pair of electrons are there around the central atoms. Here you see the dot and cross diagram of ammonia with a nitrogen at the central point. With here's a pair of electrons, bond pair, bond pair, bond pair, and here's 1 lone pair of electrons. And for water you get 2 bond pair and 2 pair of lone pair of electrons around the central atoms. And if we compare the dot and cross diagram of ammonia with dot and cross diagram of methane, we get a very little difference, which is the lone pair of electrons. Here we get around the central atom 4 pair of electrons. We also get this around the nitrogen atoms 4 pair of electrons. Here from the shape of the molecules, if I remove this bond as well as the pair of electrons, these 3 bonds will certainly no more like this. They will be at the same plane, because this pair of electrons no more repelling them, no more suppressing them downwards. So this would be certainly a planar shape. But if I remove this bond, keeping the electron here, then these 3 bonds will still be like this, because they are being suppressed by the electron pair, which we call lone pair of electrons. We get this in ammonia. Here we get 3 bonds, unlike methane, but in case of the other bond, we have this lone pair of electrons. This lone pair of electrons is still suppressing these 3 bonds. So these 3 bonds are still like the 3 bonds here in methane. The lone pair of electrons have greater repulsive power than the bond pair of electrons. So here, because of greater suppression, greater repulsion of the lone pair of electrons, the bond angle reduces from 109.5 to 107. I can explain the shape of water molecules again comparing with the shape of methane here. Look at this again, methane. This was methane with 4 pair of electrons equally repelling each other. And in water, if you remove 2 of the bonds, here these bonds being removed, and this gets the shape of ammonia. If I'm gonna remove another bond and leaving the electrons still there, then these 2 bonds are still like in 2 bonds. And with a valence pair repulsion theory, we can explain the shapes of phosphorus pentachloride, which you get Trigonal Bi-Pyramidal. Here you see the dot and cross diagram of phosphorus pentachloride. This you get 1, 2, 3 bonds at the same plane, and 2 other bonds. One is below the plane and another would be above the plane. Look, this is certainly a pyramid above the plane and another pyramid below the plane. So we say this bipyramidal. And another is sulfur hexachloride. We get the dot and cross diagram, sulfur at the middle with 6 pair of electrons. If they repel each other equally, then they will keep maximum distance. The maximum distance would be here 90 degree. So each of the bond angle we get here 90 degree. Here we get 4 bonds of sulfur at a plane. Here 1, 2, 3, 4. These 4 bonds at a plane, and 2 more bonds. One is above the plane and another is below the plane. So we call this shape octahedral, or we can say square based. Here is a square based bipyramidal shape. Now let's draw the shapes of 2 organic molecules. Here is one ethanol and here is one carboxylic acid. Here the first one, CH3. CH3 means carbon is bonded to 4 different atoms. When carbon is bonded to 4 different atoms, that certainly get tetrahedral shape. Let's draw the tetrahedral shape for the first part. This is for CH3. Here you get in the middle another CH2. Here this CH2 also has 4 bonds around the central carbon atoms, which is another tetrahedral group. Look, this is another tetrahedral group with each one having bond angle 109.5. This is one tetrahedral, this is another tetrahedral, 2 tetrahedral groups together. And finally waste. Waste means this like water. Here it certainly has 2 electrons, 2 pair of electrons, causing this bond angle same as in water, 104.5. So this is the shape of ethanol. And now I'm going to draw the shape for carboxylic acid. Here you see same thing, CH3 means this part is also tetrahedral. This is not hydrogen. Next atom is carbon, and carbon, this is not tetrahedral because this is CO. This CO means carbon and oxygen double bond. Here we get carbon bonded to an oxygen atom with a double bond, and the other is another oxygen atom. So this is the middle part of this diagram of this shape. The middle part is trigonal planar, because though carbon always gets 4 bonds, but here we get carbon having a double bond, which means that carbon actually showing here 3 bonds because these 2 bonds are close together. So totally 3 bonds are spaced around these carbon atoms. And finally waste, which is like water with 104.5. Here around this carbon atom you will get a bond angle approximately 120 degree, and here it's certainly 109.5. These 2 are 2 examples of organic molecules. We have shown their diagrams, shapes, and we cannot name their shapes because they are complex shapes. Here each of the shapes, each of the diagram consists of both tetrahedral and bend shape together, and this having 3 different shapes, 3 different unit shapes together. One is tetrahedral, then middle one is trigonal planar, and final one is V shape. So altogether this doesn't have any particular name of the shape. And I think this video has made your concept of shapes of molecules very clear. And if you really like our video, if they really are helpful for you, then just stay with us to get more of this type. Thank you very much.